modeling. So what the LLM itself do is like in most of the time they go into internet and basically search a large amount of data, and then they use the LLM to train the data into the LLM so that they can embed almost all the vast majority of general knowledge in the internet. However, for engineering, we have a very specific task we want to do and some of the design work, and it may not be specifically embedded inside the general knowledge of the internet. So when they train the large language model, it may not have the specific knowledge that we want to address in our own particular engineering design discipline. So the technique we want to use, there are a couple of methods. And so the two most common method is the first one, which is called retrieval augmented generation. Essentially here, instead of asking the large language model a question and then expect it to give you an answer, instead user start a query to the chatbot itself. Instead of going into a large language model to retrieve the answer, the chatbot now will specifically go into a local vector database where the information will be specifically retrieved from based on how close the vector database information is close to the query answer. It will try to locate the information that's closest to a query and pull that information out from the vector database, and then now we feed to the large language model to generate the desirable output. So this is so it's all almost like you have a specific answer for a student, the questions, and then student in general cannot do it, but they say, okay, read the textbook, and then the student will read the textbook and then retrieve the information and give you the answer. So this is basically the same concept where the large language model may or may not have your specific domain knowledge, but by having prepared a vector database specifically on your own domain knowledge, you can actually then generate the desirable information through querying the particular information that you want it to read and answer to you. Another common technique we do is what we call fine-tuning. So obviously the large language model itself trains from trillions and billions of data out in the internet. But let's just say you have some additional information is unique, you process, and you know the question and you know the answer itself, but and there's also the amount of information is relatively small. If mathematically, there's a technique, you can very efficiently inject those additional information into the network itself through the fine-tuning. It will then actually have that particular domain knowledge trained into the large language model itself. So this particular technique is called fine-tuning, and I will briefly touch on that later on also. And finally, this is the last one where right now, I'm not sure there's any published actually about using transfer learning, but in the generative model that we're currently right now working on, we're certainly looking into using transfer learning in one of the generative some of the generative model we're developing right now, but that will be separated from the large language model itself. But it's a general technique to basically enhance the transformer model itself. So, sorry, I'm blocking some of them. So why do we do RAG? As I say, the large language model itself is trained based on a vast lot of information that basically available in the open in the internet. So it would be good for answering general question and answer. But if you want to have very specific hardware design information, it is very difficult to have publicly available. Maybe you have some proprietary information also for yourself from yourself that you don't want to share in the public domain. So these questions will most unlikely be able to answer by the large language model itself. So you won't have a very specialized type of information that the LLM can answer and do Q&A on that. And one of the most important things that why RAG is important is it is inference only. So there is no training involved. All you do is running the large language model itself. So it's very efficient in the sense that training a LLM model takes significant large amount of resources. Inferring a LLM model takes much less. So inherently the compute is very little. And there's a trade-off to it, which I will mention later on. So this is one of the latest innovation in the RAG, advanced RAG. So this particular tool is called Llama Index. Essentially, it's an LLM agent. Not only it can actually ingest textual information in the first pass, so where if you have a regular text, you can actually ingest it and then put into the vector database for retrieval by the query. It also actually have on top that have many other multimodal ingestion. Essentially, you can ingest in this example an image through a tool called Clip, where you can convert an image to text or describing what the image looks like. And there's even more ingestion through like PDF or Excel spreadsheet or compute code. So essentially, these kind of advanced ragging, they can actually take a known type of information, ingest it into the vector database, where you can now use the LLM to query and do the answered based on your particular domain knowledge. So how does it apply to electronic design? So here I want to give you an example. This is a Llama 2. So if you ask a very basic double E question, say, hey, what is the VIA stub recommendation PCIe Gen 4, right? So it's a basic question for double E's. And you can see the answer basically is complete garbage. It doesn't know what PCIe is what VIA VIA structure looks like. So without RAG, basically the LLM basically is useless. However, if you start to produce a page out of the PCIe Gen 4 design spec, which contains text and some labels, now if you go through a RAG process where you say, read this document and give me the answer, and in which case you can see now it can give you very, very meaningful answer and insight into what exactly our VIA stub link looks like. So this is exactly how we can inject electronic design or design domain specific knowledge through this ragging process. So we can actually produce a lot of design spec or our own engineering document and have the LM basically read the document and then produce a desirable answer. So this is one method that I mentioned, which is basically the easiest way and arguably the lowest compute and requirement to achieve the desirable goal to inject domain knowledge. However, let's take the previous example. If you find yourself or your group start asking the repeating similar question about the PCIe spec when you design, right? So now you sort of have a very common set of question and answer. You start to see within the domain that you try to work on. Then in other words, your domain knowledge and query become very stable. So you know what kind of information they typically get asked and what the answer is. Then now you can start to build a corpus of question and answer pairs. And so it will become if you start to build a lot of questions, and at some point in time when you start to exceed a few thousand of these question and answer, now you can start looking to fine-tuning the model. In other words, instead of using a inference only solution where you just say, okay, go read this document, give me an answer, which takes time and the latency is increased. You can directly train the fine-tune the large language model to actually directly answer your questions. So here is what we call fine-tuning, right? Now you can with fine-tuning, you no longer even need to access the vector database to get the answer. So obviously the response and latency will be faster. Now there's a technique which is called Q-lower, which is basically a very, very mathematical efficient and low overhead way to basically fine-tune a large language model. Obviously, for large language module, even for 7 billion parameters or 100 billion parameters, you're going to need hundreds of GPU server to basically train the model, right? So pre-train, it takes thousands of GPU hours. So obviously, not everybody can afford this kind of hardware and things. However, this concept of Q-LoRa allow us to very efficiently to do these kind of things. So at a high level, what it actually does is instead of just providing the regular model where they have the full weight of the large language model itself, you actually proliferate the large language model by a small proliferation, which is what is called the low rank matrix does. Essentially, low rank matrix actually consists of a row and a row index and column index. And when you multiply the row and column index, you generate essentially a weight matrix, in which basically these are small quantities that you can actually proliferate into your entire full network. The entire network get proliferated. So it is, you are really adjusting the full trained network itself. However, you're limited by only using the two vectors to describe your problem. And on top of that, these vectors can be quantized into a much smaller quantity because these are only small perturbation, right? So you can actually, instead of using the full 16-bit weight, you can actually use a 4-bit quantize. So these are very, very small and low footprint kind of vectors. And by doing that, essentially, you can actually modify the trained model with your domain knowledge. And then your domain knowledge is actually locked into this low rank matrix where it will represent your additional information, your additional knowledge. So anytime you run your new model, you add the weight with the low rank matrix to prorate the trained model to get to the desirable your model and result you want. Now, this has actually also additional unique advantage, because first of all, the computation is very low, and in typical case when you want to fine tune a for example a Llama 2, maybe 7B, or you can actually fit the amount model into the single GPU in the lab in your server. It's mathematically very efficient because it's 4-bit, and also the matrix size is rather small, the vector size, and so you can compute maybe in a few hours to fine tune a large language model, even with a single GPU itself. And so this is something that you can quickly do and experiment yourself. And another advantage is, let's just say your training material is not perfect, and there's a common large language model called hallucination. So your quality of data is not that great. Your LLM start to hallucinate. So which means they were answering garbage, right? So in one of the toughest questions you have to tackle is, what if your model quality low, and then the LLM itself, after training a couple thousand hours, hallucinate and give you garbage, right? That's not good, right? But how are you going to unlearn the trained model, right? Once you already train in, the weight is already embedded. You cannot undone it. But if you do it in the LoRa, all you need to throw away the LoRa, retrain the LoRa, fine tune the LoRa itself again. So you can continuously improve the LoRa without disturbing the main large language model. So this is one way of very tailor your solution and continue fix your problem and improve your quality. And one thing unique about LoRa models, you can actually, because it's an additive process, you can just keep adding probation into the LoRa model. So you can actually fine tune model, because you can just keep adding this additional term to correct new knowledge, right? And also in terms of security, because all the information, your proprietary information, new information is contained within the LoRa matrix, you can control whether those information is within your company, released to public, or limited to a certain department by just limiting the access to this LoRa matrix. The large language model can be actually sit in public, maybe in Hugging Face or somewhere somewhere in the open. It doesn't matter, because the large language model will never get touched by your proprietary information. You can always control your proprietary information. So from a security, convenience, and usefulness point of view, LoRa is one of the unique and very advantageous tool that you can actually use for fine tuning. So in other words, through RAG and LoRa, so far what I have done is to sort of give you a roadmap to how you inject your specific domain knowledge, right? So it can be proprietary, it can be public domain, or it can be an open spec that the LLM doesn't take care of. You can inject this domain knowledge through this kind of process. So now we're at step one of a current kind of application in LLM for design, right? Which is basically do a basic Q&A. So people call it co-piloting or assistants or things like that, where a typical application like customer service, right? So you train your service engineer to when field question, you can give an answer through the LLM itself, or you have a tool designed that you want to have certain help menu, right? So these are perfect for Q&A kind of things. So you already inject your domain knowledge into it, so which is the advantage, right? So what if we start to go next step where we say, okay, now can we ask the LLM start to do some kind of reasoning and learning? So this is where the next step of application of LLM is, where we call that chain of thought reasoning, right? So here in a typical fashion, in a normal Q&A and LLM, you ask a question and you expect the LLM to give you an answer, right? So those are normal Q&A application. In some cases, you might want to give a multi-prompt, which is essentially what you start with a question and give an answer, another question and give an answer. So sort of have the guide the LLM to sort of figure out, okay, if you have this kind of question, how do you answer it? What direction? But another much better way to do it is through what we call chain of thought. So instead of asking a question and directly expect an answer, you actually break the question into small parts sequentially. So do this small part first, get an answer, and then from that answer, tell me ask the next small question to get the next answer. The next answer, ultimately, this small little step eventually get to your answer, right? So this is essentially what they call train of thoughts. So in this case, this example is like you do a standard prompting, you ask a mathematical question, you give an example, the answer is this, and then you ask a new mathematical question. Essentially, the answer is wrong, because basically it doesn't really know how to follow the problem, right? So instead of that, you have this train of thought where you start asking a question, and then in the answer, you give an example where it actually answer the small question, followed by another small question, followed by a small question, ultimately get the right answer. Now, when you ask the same question, new questions, the LLM itself start to follow the chain of thought and try to derive the right answer for you. So essentially, this is how you can sort of nudge the LLM to start to do reasoning and do learning and thinking by itself, right? So now that leads to an interesting proposition. So remember, now we now can have the LLM start to have reasoning. So now we will introduce the concept of LLM agents. So in this case, so agent, essentially at a very high level, think of an agent as almost like a regular CPU, right? It's a brain, right? So the LLM itself is a brain as an agent, right? You can do something called planning. Essentially, just like the analogy is like you have a little program that you expect the CPU to do, right? And then you sort of have planned the LLM agent to do something that you want, right? And how do you get the information? Now, instead of the LLM itself have to have the information, you can sort of like almost like, again, like a CPU where it has I/O, where you do in and out and then execute certain things. In this case, it's already very well known that LLM can generate API and control API. So pretty much any CAT tool program, you can actually synthesize Python script or API to directly exercise a tool. So imagine here the LLM now can actually use the API to exercise tool itself to retrieve the derivable result in a multi-step process, just like what I mentioned, the train of thought, right? So you have a train of thoughts, and then the LLM itself just getting the answer step by step by itself, it actually execute a tool and get partial answer, right? Now, in addition, just like a CPU in the processor, you need to have memory, which means that when the LLM itself go through the action of doing the tool, you want the result that is observed to be able to store into a memory area. So this is where the new additional information from the LLM comes from, because this new concept of agent also outside of the LLM itself, it provides a scratch memory area where we can store its observation and then access it and retrieve it and do things later on. So if you tie this all together, you start up with the planning where you tell the LLM what you start to think, the train of thought, and then the agent, LLM agent, will start executing tools to get the desirable result. Along the way, when they get the result, they store in the scratch memory area based on this observation. And then ultimately, as you accumulate all these observation exercise, it draw the right conclusion and answer and give it back to the user query. So now you sort of like the LLM is almost like a baby CPU with planning as a program, with tool as an execution unit, and with the memory areas to store your observation and prepare for your execution. So this is one of the example. You start with query, and then the agent keep exercising the tool, and then keep the observation in memory. After a while, it get the right answer, and then it will respond to the user, right? So here, this is an example where we use the LLM again to exercise some of the tools. So here, the exercise we ask the LLM to do, read the design spec to discover what is the transmission line parameter looks like. And so the first action it does is read through the transmission line parameter, right? And then the second step is go do, okay, once you get the parameter, go feed this information of a transmission line geometry into an API where the API will exercise and initiate a simulator to do the simulation of a transmission line. And now give me the answer what the structure look like. So in other words, the train of thought here is like you can ask, you can RAG or most likely RAG a design spec from Intel or AMD or somebody else. And then they will give you the structure that you need to analyze. And then you take those structures, the LLM will take those structure and then use the API agent to issue those parameters into the simulator. And through the simulation, you get back the answer, right? So sort of now the LLM now, like I say, you start from Q&A, now it's actually performing engineering tasks for you. So it's actually start to do reasoning and performing tasks for you. So this is the next step. In this example, you can see basically it retrieve the transmission line, one of the transmission parameter, and then feed into the API where it calls out the simulator to do the analysis for you for the transmission line. So now, if you now have this idea of so if you now have the idea of doing execution as an agent, what we do something even more, one step further. Instead of just doing a task, I lost my mouse. Okay, so you start to create what they call meta prompt, where you can actually create what you call optimization LLM, where it will generate a sequence of instructions, and then you will execute the instruction through maybe a same agent or a different LLM agent to basically execute those simulation tasks. For example, you give the optimizer LLM will issue a various combination of geometry, for example, and then the scoring LLM agent will execute the simulation analysis and get the result, and then evaluate certain target, for example, target impedance, for example, right? You got a different kind of score, and then feed it back to the optimizer LLM. So here you can actually continue to do this kind of process with a specifically desirable optimization scheme. Pick your own, desirable optimization scheme. I think the Google paper, I think their scheme recommendation is do a salesman, puzzle, right? So find the shortest distance, and also there's a linear regression example. So you can sort of use your own favorite optimization scheme, and then using optimizer LLM to just continue looping between a sequence of instruction, get the score, and then eventually what you think you can do is based on the score, you can finally locate the optimized desired point, in which case basically the optimizer LLM will issue the optimized instruction, and you got the optimized solution. So this is a very rudimentary method. You can actually start to doing design which is what we call optimization by prompt. So in other words, here you are now truly using the LLM itself to do a designing task. It's not just simple assistant or Q&A or just simply do a dumb simulation. Now you're actually expecting the LLM to actually do some design work for you. So that leads to what I call foundational model for SIPI. So this is very timely because as I was preparing the slides, this is something that I thought that's the future, but this week ChatGPT announced like GPT 4.0, right? So now it's truly multimodal, right? So previously we heard rumors of this multimodal because up to now we would only talk about large language model, text. So now at least ChatGPT now have capability of ingesting directly text, images, not only images, moving videos, and speech. So at least these three now can be tokenized by ChatGPT directly. There is no more translation. You don't need clip to translate your image into text. There is no more translation between speech to text. They can directly tokenize these images and speech and text into the LLM itself. There's no more, because of that, to do the latency, right? So this is the part where I suspect this is where Apple is coming in. I suspect the Apple iPhone, all the CPU processing unit will be one doing the tokenizing. So essentially like a division of labor where the iPhone itself will do the tokenizing and feed it into the cloud to do the LM, to do Q&A or do whatever is desirable. So now, once you have this foundational model or LM, then let's say this is the encoder part, then you can use a decoder, like custom decoder that can actually do Q&A, sentiment, or all kinds of things you do. So here's what we think we want to build the foundation models for SI and PI, right? So here, at least in HPE, we sort of have a vast lot of design spec from all our vendor people we work with, Intel, AMD, Broadcom. So a lot of design spec has been documented and provided to us. So we have huge history and library of these design guide. And obviously we also have our own design spec, right? So for example, most commonly, we have our own stack up, we have our own documents say, hey, how we ourselves implement this stack up, geometries and transmission lines, spacings, all the rules, right? So, and obviously our manufacturing partners also give us ODM, also give us some design rule, the DFM spec. So all these things are very well documented with our knowledge, right? So what if tomorrow we ingest all this information into the LM? So now we tokenize all this information. Now, so we can encode this into embeddings. So now we can decide, once we take this embedding, what can we do out of it? So now, once we do the encoding, right, with embedding, now we can sort of think of, okay, in the foundational model, what we can do to take advantage of it, do works, right? So some example in the decoding part, through the LM agent is what we call, this is simple, or we always sort of demonstrate it. So, okay, you can actually take this embedding geometries and things like that, and then you can fire up the EM simulation tool, simulate and get your result, right? So that's a basic thing we sort of demonstrated already, right? And we're currently working on this optimization by prompt thing where you can actually use the simulation result and use multiple agent, multiple prompt, and then eventually we can use LM itself to drive the optimization and get the desirable result, right? So now you have these design document, you can do simulation, you can do optimization, the LM will give you the right answer. What's the next step? Now you can actually, you can actually use this desirable result and tap into, for example, a board routing, which is what we call constraint manager, right? So we can actually feed those desirable geometry, maximum length, minimum spacing, everything that we simulate and optimize. You can easily generate the design constraint file. So that's a pretty straightforward exercise, right? So now you can sort of design these, and obviously the last step is you can actually use the API to do the overrouting. So you can sort of see that the foundational model itself, the concept basically is to gradually, if not at this stage, there's no talk of replacing human or engineer, but at least we can do this kind of rudimentary work for an engineer that help, so the concept is co-piloting. So co-piloting means essentially you are basically doing some basic work that the engineer will do, and then you use the LLM to do these things for the engineer so that they can be more efficient, right? Now, all these things work great, but one of the particular problem with AI in particular in general, and is you can in design if you have to train you basically have to do a lot more simulation analysis to train a model. So the work, the output and the amount of work you put in is always more than you just do it yourself as a human, right? So let's say there are papers that to model a transmission line you have to model like a couple 100,000 cases. If that's the case, then you might as well simulate it one time and then you get it over. Why bother model? But the point of this foundation model is like you wanted it to be able to go forward, and it's something that you can invest upfront investment, and then in the future you can future-proof your design, right? This is where one of the things that we also start looking into is this whole concept of fine-tuning. For example, like I mentioned, LoRa is one way to very efficiently fine-tune a model. So in this case, what if we have a simulation model? Also, when you have a speed bump, can we just use fine-tuning to very quickly and efficiently improve the model so that you can go forward into you invest the money and analysis for your current generation design, and then you can speed bump in it to get a better result in the future, right? So that's one way of doing fine tuning, right? So this is the part where I mentioned transfer learning, and there's so far no example, and this is something that we think that's the right direction. Is you also want in future proofing, you not only you're gonna have a frequency change, you also have feature change also. Let's say you start with a very simple differential VR model, and then as your speed go faster and faster, your model become more and more complicated, right? So what do we start using also transfer learning, where we start off with a simple model, and then when we want to have a more complete model, instead of rebuild the whole model again, we sort of add a few layers in the model to accommodate the new feature and train only the new feature area with the new extra layers. And so now we can sort of increase the complexity to future proof it. So this is the part where we're doing transfer learning. So again, this is something that we think that how these kind of large language model and generative AI can really help us in the SIPI community to start sort of building this kind of foundational model where we can future proof ourselves, and then also we can automate a lot of things through the LLM and the LLM agent itself, right? Imagine in the future, like if you look at right now, a typical Intel design spec is about 1,000 page. If you look at AMD, maybe probably in the 400 to 500 pages. So these are things that if just the fact that you can rack the whole spec and and embed it into a particular embedding that you can take advantage to generate your simulation, this by itself is already very valuable, right? So now okay, we touch on using the LLM, and we touch on how the LLM will be used, and then we also touch on the foundational model concept. So now we switch back to, okay, now we have this tool, right? Does this tool always have to be some kind of CAD tool or EDA tool, or can we actually tap into generative AI to actually do the tool become the tool itself? So this is one that where I think in the previous IEEE meeting I already sort of presented. So I'm not going to go into detail, but I think there's a couple of published paper my team member have published that you can actually trace back. And essentially, this is an older generation of generative AI, and in this case, we were not using transformer, and we were using encoder decoder architecture called UNet. But right now, we sort of in the process already have done to pass it into transformer. So we know transformer based also work, but the architecture is very similar in a sense that basically you take a input waveform, and then you can turn it into an image. And then we use what we call GAN, which is generative adversary network, where essentially you have two kind of competing AI. One AI is to keep generating a fake image. The other AI is to tell it's the discriminator, where it tell it's a fake one or new one, it's a real one, and then you train yourself so that the generator generate the fake image so good that the discriminator cannot tell, and then you call yourself a converged solution, right? So here the fake image is actually the output eye diagram of the high speed, in the PAM4 30s. And what you try to do here is to train the generator so good that the discriminator cannot tell whether it's a real channel simulation result or actually it's a fake image. And so this is actually the result. This is fundamentally what we call a digital twins. It's not just a simulation per se, because obviously, there are already existing tools, CAD tool that actually generate the result, right? So you have a waveform coming in, you give you an eye diagram. That's a pretty standard simulation tool already. However, digital twins itself has two distinguished difference between the simulation model we currently use in EDA tool versus the digital twins. One obviously is this whole generative model concept, where if you build a generative model, you can stuff an unseen channel condition into it. If it's within boundary of the training spectrum, it can actually give you the right answer most of the time. And so this is part where the generative model they can cover unseen condition versus a model where you have to explicitly model the channel condition before you do the simulation. And the other thing also is very important, the difference between the digital twins and at least our point of view of digital twins versus a simulation model. Digital twin inherently is fast, right? So in this particular example, if you want to simulate some kind of IBIS model or simulations, it would probably take you about 8 minutes to generate from an input waveform using a CAD tool to generate an eye diagram. In here, if you take away all the graphics, things like that, just to generate raw data, it takes about 230 milliseconds. So it's significantly faster. So now it actually opened up some very intriguing possibility. Because now if digital twin is so real time, what if we start tuning the circuit, the real circuit in real time with the digital twins? So now it opens up not only a simulation aspect of the digital twins, with enough compute power in a system, when you bring up all the high-speed channel, you can actually use the digital twin itself to tune the circuit rather than relying on a fixed algorithm, typically or 30 used to convert your solution. So this is one of the things that we are looking, seriously into, the whole aspect of this real-time application of digital twins, right? So another things that digital twins is good as, because it's data driven, it's not physics based. So it's actually relatively easy to tie multi-physics problem. So here, what we have is we take another example where we have a power image of a similar power analysis. We have a thermal output of a thermal solution in the system. Because it's not physics based, it essentially you just use the same way to train the digital twins as if an electrical. Because all it cares is image, right? You fake an image out, fake an image out, in, and so now you can actually relatively quick to generate a power to thermal image. So again, this has a huge link up into, for example, in the future where we have electrical to optical analysis or power to thermal analysis, which in the current state of our design, a lot of things start to intermingle. You have optical mingle with the electrical, and then you have a lot of thermal design tied into power design, right? So this is exactly where another area where these digital twins are very useful, right? So this is one of the examples where you can see as the left-hand side current and power changes, the thermal response of the true heat map ground truth versus the generated heat map is almost indistinguishable from each other, right? So let me momentarily stop the sharing. Let me bring up now. So this is actually a live demo. So the slide I presented is just animation, right? This is actually a true digital twin right now running in our server lab. So this is just a regular HP server with a single GPU, nothing special. So what you're seeing here actually is a digital twin running in the background with the trained unit. So if I change the channel condition, you can see the eye diagram dynamically changing. This is actually go through the simulation itself. So the background unit is actually doing simulation generating eye diagram. So this is actually so as you can see, the channel loss is increasing, the eyes start to shrink. And then as you can see, as this channel gets shrunk, I can turn up the equalizer and the eyes start to open. So this is actually a real-time running. It's not an animation or loading image. This is actually and most of the display, most of the slowness of the display is controlled by first of all, we have an internet. Second of all, the image itself takes time to load. If you look at the raw image itself, it takes about 200 something milliseconds to generate the data itself. So and then if you compare with any PAM4 simulation using regular CAD tool, it will typically take about 5 to 8 minutes to generate a PAM4 eye diagram. So it is significantly faster in speed, right? So here is another demo where you can sort of see, assuming you have two current power source, right? So current, and then you can see as the current goes up, the hotspots start to heat up, right? Please. Okay, so you can turn on the fan and you can see the thermal start to cool down, right? So now you can sort of, as if the power goes down, you can actually drop the fan speed and it'll be okay. So imagine, again, this is actually a real-time simulation. There's no image loading. This is actually as the power condition changes, the unit actually adjusts to itself to get the right answer, right? So you can imagine you have an iPhone that you know where each of the hotspot is, right? You know what individual component power consumption is. Now you can input the power in real time, because it's easy to check what the power is. And then you can use a digital twin to tell you exactly what the cooling solution is in real time, right? So this is where these kind of digital twins will hopefully in the future will help us, doing design, sort of help us basically solve complex engineering problem, not only in the analysis and design phase, also in real time, we can sort of help us do this kind of address this kind of problem. Right? So, okay. Okay. So go back to. Okay. All right. So this is basically what I want to share to you today about the whole application of LLM and generative AI. Hopefully, again, we come from a very specific group, SI doing SIPI. I don't want you to limit yourself to, oh, this is just a solution for SIPI, but rather, basically, we believe this is a general engineering technique where we can use the LLM and use generative AI to tackle some of the engineering problem we have. And so, to sort of conclude what we can say right now, we're still learning. So definitely this whole LLM design for hardware is a work in progress. We still, there's a lot of things that, we're still working on things, and hopefully in the future we got results, we can share more. The model is changing very rapidly. Like I said, in the beginning of the week, I have a lot more things about, multimodal. Sorry. Let me see. No. Okay. Oh, I know it. Okay. Okay, that's okay. I'll just use this. Yeah. So um so I think one of the key things is like this week we have the announcement of GPT-4, right? All of a sudden we have multimodal become reality. So everything I was talking about, we're prepared to say in the original slide, half of this is gone, because basically right now we don't have to worry about that anymore, because now we can process image, we can process text, we can in fact, if you think about audio, essentially it's just tokenizing time series. So a waveform now can be tokenized. What it really means, you can fine tune and a waveform into LLM, right? So the possibility now also change yet again, right? So this is something that the way we ingest information now also change. So this is something rapidly changing, and we try to catch up. So hopefully we learn more as we have more access to. And ChatGPT kind of difficult, because most likely company will not allow us to do, but somebody will catch up something with multimodal and then in open source, and we can do it. One of the fundamental thing, most important thing is like the quality of the raggable design spec is very important. Everything starts with good data. So this is one that actually called to the industry, and hopefully we will, as we gather more and more interest to the industry in general, is like right now most of the design spec are not raggable. For example, there's no way I can reg a waveform. It will be very challenging to reg a eye diagram, for example. Right. Some of these things we have to basically work together with the industry, or at least the vendor, say, in the future when we write design spec and we make things more reggable, maybe just a helper paragraph, just say, okay, you have a diagram that for human, and then you have a small paragraph say, this is what the diagram describe the spec, how it look like, and then let the reg the helper paragraph instead of the picture, right? Now, finally, this is one of the things that more interesting, right? My friend, I just talking to him. It turns out that this is a new paper that Stanford researchers start mentioning. It turns out there's something called emergent ability. So essentially, what people observe is when they train this large language model, the ability of these large language models start out with very flat with a certain capability, and after your model size and your training exceeds certain limit, all of a sudden the capability shoots up to exponentially growing, right? In some of the things like math, I think there's a train of thought and all these things. The ability of the LLM model, once you cross certain size and dimension threshold, the knowledge becomes very good, right? Now, granted that right now we're working on engineering knowledge and design, there's not really a very specific tailored LLM for engineering, right? So we're just still circling around the peripheral of the LLM, right? So all our ragging, all our fine tuning are really trying to retrofit a generic model. The only one I'm aware of right now is NVIDIA, right? NVIDIA, obviously, there's something called Chip Nemo, where they actually pre-train the model because they can afford 1,000 GPU hours, right? So NVIDIA actually, you can see and hear, they have an aspiration to actually do the design part, because because it's free for them, right? In order for them to design, they have to do it themselves internally anyways. Might as well sell the model because they have the domain knowledge. We don't, right? So some of these things are interesting in the sense that if you do the math here, right, this is roughly about 10 to the power 22 flops. And if you do the math roughly, if you have the regular state-of-the-art cluster of GPU, for $3.5 million, you can train it within 1 month. So as a company, as a group, there's no way I can do it. But if you think about for an EDA company, something like the big three now, it used to be big four, but now it's big three. This is well within the budget. So they can, and then they have quality data because they have so many design in themselves, right? So this is very, this is sort of like an aspirational thing in call to action for the EDA business is maybe at the end user may not be able to do it, but you have the resources and budget, potentially pre-train a engineering only LLM, and where you can basically, do the emerging capability for engineering. For EDA, from the EDA business, it is well within the budget. $3.5 million is not that much for EDA business to do R&D, to have the capability, right? So with that, I will be open up for questions. Thank you.
Well, thank you, Chris, and we're open to questions.
Okay. So for that, we have two different types, as of I know, two different types of storage units like vector index or using knowledge graph. So can we use knowledge graph to predict system designs when it comes to chip manufacturing and everything?
I believe that's like basically what
Could you repeat the question
is
because
instead of vector database, you use the knowledge graph to represent, and so that basically when you do your ragging, you can rag the knowledge graph rather than the vector database, right? I believe that's where the IC people are doing, right? That's why I in the beginning of my talk, right, I was this one. I'm doing high-speed design, right? So we really don't do chip layout, but this is something that we actually look into because also for PCB layout, that may be potentially very useful. In fact, when I talk to some of the NVIDIA, the researcher, right? So they're very focused on the IC. So they're definitely looking into some of these things. But they mentioned also, actually, it turns out the most difficult problem for routing right now actually is PCB. And we also experience very, very difficult problem. So yeah, that's what we potentially one of the things that we can help. Yes.
Another question is that when it comes to chain of thought and if you're giving some examples in the prompt, so like it's basically the same thing. It's just that you're automating or giving some examples in the prompt directly. So like if you're giving some generalized versions of examples that covers a different aspect of your domain, isn't that the same thing as automating your prompt as of asking you to the user directly?
Okay, so the question is basically when we talk about chain of thought, then isn't it just the same way of just asking a couple of questions to get the desirable answer, right? This is true, but remember the aspect of LM agent is now the question and the answer is breaking down into different parts, first of all, right? So you have multiple questions, multiple answers. And the answer is actually not derived from the LM itself, but rather LM issue the API to run tools to get the answer, right? This is the part where engineering comes in because now you can ask the LM as a brain to control the simulation engine, right? In our case, simulate the 3D EM tool to generate the answer, right? So that is this is beyond the regular train of thought, right? The regular train of thought is everything, the knowledge contained in LM, at most maybe you rag it, right? In here, you actually take an action. There's additional action, an observation, right? And then not only that, you store the observation in the memory. So now these are the new aspect of LM agent on top of the train of thought. Train of thought is a basic planning stage where you use a train of thought as a basic planning. But the desirable action, observation, and memory is actually is where unique about AM agent versus a regular train of thought. Does that answer your question?
Yeah.
Hey, Chris, very good presentation. I have two questions. So first one, can you go back to the slide? I forgot the number. Basically, you talk about the vector database.
This one.
The next one, you have one show the vector database and document. I remember
this one.
Maybe the first one. up one more, like page 5. I think it's page 5.
Page 5. Okay.
Yeah, page 5 here. So I see you have a document and vector database.
Yeah.
So my understanding is once you have document, you will vector database
Yes.
first. Just do once.
Yes.
Then you don't have to repeat it, do it, right? Okay. So
In the LLM language, the lingo, they call it embedding. So you want to convert the text into the embedding. So embedding is the basic level is just basically create hash key,
that's
right? Multi-variable hash key.
okay. The second question is you probably hinted somewhere about, let's say, if I have already trained a model, for any reason it didn't give me the right answer. So what is, I think there should be like a typical people call the human in the loop or feedback loop to be able to help you fix the problem. At least the same problem happen again, it will not repeat. Do you have any thoughts or comments on the how do you basically be able to provide feedback and be able to improve your model over time, make it better and better over time?
Well, at least our current approach is like we try to cheat, right? So we rack it.
Okay.
Right. So like I say, if you rack it, then you know for sure this is where the information comes from. Right.
So, but the rag is how do you rag it? Let's say, for example, you give a question or a task, and then maybe give you the wrong answer. But how do you know like where is the problem happened, or how do you? What do you?
Right. So this is an example where we break the question into multiple parts, try to get the right answer. Right.
So basically, you have to break down to see where is the problem that go to there to rack that section to fix the problem. Okay. Very good. Thank you.
Hey, Chris, can you go to the slide where you showed
I'm hearing somebody saying something. Let me. Can you speak louder?
Yeah, can you hear me now?
Yes.
Can you show the slide where you showed the optimization of the PAM4 channel? I think it was.
Okay, so the question is, can I show the slide where I do optimization of the
Yeah.
PAM4? Is this
Yeah.
the slide that you're asking?
Yeah, and slide 13.
Yeah. Okay,
So-
what's the question?
My question is, so is there like did you have to use, again, I'm not expert in this, but I'm trying to understand if you have to use any LLMs underneath this whole when you train this image-based models?
Okay, so the question is, in this example, do we use LLM? No, that's why I sort of separate the aspect, right? We have LLM application where we drive the agent to drive the analysis. This is actually LLM. This is a Gen AI tool that we expect the LLM to use, but it's not an LLM. This is actually a generative model to replace the simulation tool that we're currently using. So the question basically is it an LLM? No, this is not an LLM. However, if you watch Andrew Ng, I think he made a presentation in AI, some kind of venture or something like that. He mentioned that it's a 10 minutes presentation online. It's very famous. Everybody, I think a lot of people quote it. So he sort of started to mention something similar. Imagine right now the GAN engine we actually use is actually have two AI, right? One is generated the generator, the other one's called discriminator, and they compete with each other to generate result, right? What Andrew Ng actually mentioned in the future, he believed what LLM agent will do is they have two agents. One LLM agent is to generate the result, the other agent is critique. That sounds awfully like GAN engine itself, right? So I think right now, potentially, these two techniques will merge at some point in time. Right? And also remember, like I say, once we go into the realm of ChatGPT 4.0, we are talking multimodal, right? So the input waveform itself can now be actually the so-called token can be tokenized, right? The output image itself can be reversed out as an image. How is it different from cat and mouse? They don't care, they don't know, right? This is part where you potentially can fine tune it into the train model, right? So this is basically, even though right now, to answer a strict question, this is not an LLM, but in the future, we can adapt the LLM to do something similar. Right?
Okay.
So does that answer your question?
Yes, thank you. Yeah.
Okay, thank you.
So along the same line, for GAN, have you seen anyone actually use transformer instead of the
Oh,
gap,
gaps. But the question is, in the GAN side, have we used transform? Yes, we already moved. This is a very old presentation
Mhm.
and old paper we wrote, right? So at that time, we're using that, but we are at least some aspect of those things we already move on to using transformer.
Yeah, kind of makes sense. Yeah, thank you.
And transformer is a revolution, I think.
Yes, but I have to defend UNet for a while, okay? You can't train a transformer with one server, with one GPU. There's no way you can do it. But I can train a GAN engine, these things. Everything here is just trained by one server, one GPU. You cannot do the transformer training. So we have a champagne taste with a pizza budget, right? So this is how we do it, right? So there's a famous word, right? The journal go to battle with the army they have, not the army they want, right? So we're tasked to do this thing. So I don't have racks and racks of GPU. I can't train the model, transformer model. Right.
So is that because of the technology, or do you
transformer
think?
just on the time series should not be that expensive, right?
Yeah, and then that's also one thing on the transformer in the time series, right? So
I guess the future, right? It's not now, it's going to the future too, when cost comes down.
actually the correct thing is like we were actually not looking at transformer. We were actually seriously looking to stable diffusion. That makes more sense. Right? Stable diffusion is really a text to image application, right?
Mhm.
So
Exactly.
in this case, well, you can still see it's a transformer, exactly. It's a stable diffusion is a decoder, kind of, transformer, but stable diffusion is actually what we're looking. But now that we with GPT-4, we may not even care about stable diffusion, right? And stable diffusion is a very known problem, which is basically, in order to train a stable diffusion, you need 5,000 GPU hours. Again, I don't have the money. I'm sorry. So, does it answer the question?
Yep.
Okay, thanks.
One question, make sure I understand this example. So you have input wafer,
Yes.
you have input gas. Is this like you just translate the one-dimensional data to a two-dimensional
Yes.
input and be able to? So can you skip the middle one, just have the one-dimensional input and get the two-dimensional output? I think you can, but I'm just curious about why you pick the
Well,
middle side.
the short answer is when we start doing this investigation 5 years ago, again, is the only thing we know. Brayman angular field is the typical thing that people use. That's how we started, right? We were learning a lot, and in particular, my credit to Priyank Kashyap. So he developed all of these algorithms, right? So we started with just the image-to-image UNet, right? And now with the transform, yes, you can actually do time series into output image. Yes, you can do that.
Okay, thank you.
Okay.
Chris,
So
can you hear me?
For the language model you're using, are you using Llama 3 or GPT?
We don't use GPT, but I'm forbidden.
Oh, okay.
So Llama is something that we can download from Hugging Face locally, and we can run Llama 2 locally in the server that completely isolated from internet.
Okay.
So that's one of the advantages, right? So
Yeah, yeah. Yeah, we're forbidden to use ChatGPT.
you can, but there's a lot of people work. And
Yeah,
then
no, you don't want
and
to set
also
trouble.
this is a fair warning, right? I'm not sure how many of you guys want to design con this year. There's a paper published about using LLM for DDR5, right? The author, and he mentioned he was using GPT, but what he observed is he started to realize that even though you're ragging it, or you doesn't, I think the GPT actually start to absorb the ingested the information.
Yeah. That's why.
So you start asking,
That's
then you
why.
start asking DDR5 question all of a sudden. So you don't know what's behind that, right? That's the thing that caution people, right?
Exactly.
So
But if you're doing RAG, the LLM should not have access to your data, right?
excuse me.
If you're using RAG as an application,
That's what they say. So the question is, GPT is supposed to be when you rag, they're supposed to access your input. That's what they say.
You never know what's behind.
You never know.
But that's why there's a reason for, well, there are a couple of reasons why we have to use Llama, right? Because like I say, right, Llama, you can actually fit a server, single GPU, and do a lot of things. I just don't have the luxury. I mean, I'm just little budget. I have a champagne taste, but a piece of budget. All right.
Chris, question. Can you
Okay.
hear me?
There's one more.
That's an online question. Sorry.
Can you hear
Yes.
me, Chris?
Yes, I can.
Great. Do you have a slide that has maybe the full citations, like for example, this one from the DesignCon at all? Do you have a slide showing?
I would try to work on it, but like I say,
Okay.
you know, I apologize. It's not a good citation in the sense that basically I can cite the author, but I should cite all the paper things. I'll try. Yeah.
No problem. The real question that I have though is going back to the QLoRa. It seems to me that one of the tests for it would be, for example, in the corpus, find all instances where one document conflicts with another. And that sort of requires an understanding of what it's reading. I think that's a real limitation of the current technologies. It's sort of a pattern matching basis of understanding. It's not really an understanding at all of what it's reading when it's reading the PDF corpus. Am I missing that, or do you find that there is more understanding beyond just pattern matching?
Actually, that's a good question. And my answer basically right now is like, we have experience in fine tuning with QLoRa. We have experience in ragging, but we have not experience in using rag to generate a data set for QLoRa, which I think is the right direction. In which case, basically, you can curate your question through the ragging process to make sure the quality of the corpus is correct, and then you fine tune it. Rather than right now, I believe most of the fine tuning you just use ChatGPT to generate the corpus and then fine tune it. And so this may answer your question in terms of maintaining quality, because if your corpus is generated from ragging, you have sort of quality control of your data, right? Sources. Does it answer your question?
Well, yeah, but even if you have quote quality control, because I wouldn't be the creator of all these PDFs, so I wouldn't have intimate knowledge of every single PDF in the thousands of PDFs, but they are all on the same subject matter. Now they can have conflicts in the sense that different researchers will come to different conclusions or different understandings of their own data. But if the QLoRa doesn't really understand what it's reading at all, it's not going to find any. It doesn't have the understanding to find the conflicts, is my problem.
Yes, and I agree with you. And this is the part where, okay, I'm going to hide behind the fact that you can throw away a QLoRa and then retrain to solve the problem. But I think if you specifically ask the question of, okay, through your corpus data set, can you identify where the misleading multi-question, multi-answer is? I believe that's the only thing you can do it is by curating your training sets, right? Because it's already boiled down to very simple, right? Your corpus is basically typically at tens of thousands, where you can basically search through your pairs and then identify which ones are conflicting, right? So that's one. I'm just trying to dance around to answer the question, but that's the way right now I think the best way to handle these kind of thing, right?
Okay, that's a fair answer. That's I thought maybe it was just a problem in my implementation or my lack of knowledge that was resulting in this problem, but apparently not. Thank you.
Yeah, you're absolutely right, and that I think this is one of the complaints I keep hearing is like, if you do analysis, you can always draw the same conclusion. But if you ask an LLM, every time you ask an LLM, they may give you a different answer. The consistency is actually quite difficult.
Thank you very much.
Thank you. Okay, so I think I run out of time.
This is Ken. Andrew, do we want to run the video again for the recording?
I can't hear somebody try to speak in the.
Oh, really? Ken and I are trying to speak.
Okay, sorry.
Can we? Yeah, thanks for your talk, Chris. Andrew, do you want to run the video for the Arduino again?
So we are done online. Thank you all for attending.
Thank you.
So I'm actually currently doing internship in HP only.
Oh, really?
Yeah, but yeah, I think it's HP INC.
Oh, I see.
Yeah. So I'm actually hired for the chat creation, creating chatbot.
Yeah, customer service, right?
Yeah.
Yeah, I know. But this is a
Exactly.
really hot topic.
Yeah. So it's really nice. And it's really interesting this domain to be in right now.
Yeah, because basically think about it, right? Your first level is with Q&A to customer service, right? But you start as an agent,
Exactly.
right? Then you can start to do something amazing like recommendation engine.
Right. So I created a recommendation engine for a e-commerce platform during my undergrad using word models and everything. Yeah. So I just wanted to get some answers regarding hallucination. So now I've seen that RAG is being used to reduce hallucination.
Yes.
But it cannot reduce hallucination. It cannot eradicate the hallucination completely.
Yes.
So that's why they are moving towards RAG plus agent.
Yes.
So is it really that is the case that
We're still looking into it. I don't know as much as I do. Because right now, this is very new, right? Agent is something very new to us.
Okay.
Yeah, we start working on another reason why. But, you know, if you can do the agent and also do the optimization, then it will go a long way to do it.
Okay. And sorry, just
Okay.
another question. So when you have one slide regarding optimizing the prompts.
Mhm.
So you're using optimizer LLM and then scorer LLM.
Mhm.
So like is there a paper which I can read?
I think there's a Google, very famous Google paper. Everybody read the same paper.
Okay.
So go check out that Google paper.
Is there any way I can connect you on LinkedIn?
Yeah, just link in, Chris Cheng and,
Sorry, what's the name?
Chris Cheng and, hey, sorry, one last slide I forgot to present. So anyway.
Is it this?
It's more like the opposite, yeah.
Very nice meeting you.
Nice meeting you. Thank you for coming by.